是数字这边的话要看字母。
Recording in progress.
大家早上好，我们今天请到Rosulek 教授给我们介绍他的这个基础方面的最后一次报告，是关于隐私保护交集集合求交的 PSI。Like I finish the very brief introduction, so you can start.
Okay, thanks, Yu. Hi, everyone. It's nice to see you all again. Thanks for coming to the last installment of this lecture series. Excuse me. Today, I'm going to talk about private set intersection. It's a special case of secure multi-party computation, and it's something that I started studying about 4 or 5 years ago, and I found it really interesting. I hope I can share some of the things that I've learned about this interesting application of secure computation. I hope you enjoy it as much as I've enjoyed learning about this stuff. So, private set intersection refers to a situation where there are two parties, Alice and Bob, and they each have a set of items. And they want to learn which of the items they share in common. So in this example, each party has 9 items, and there are 4 common items. And they want to do this without revealing any extra information. So what that means is, from Alice's perspective, she doesn't learn anything about Bob's items except that he has these 4 common items. But she doesn't learn about what any of the other items are. And then there's a symmetric privacy guarantee for Alice. So from Bob's point of view, he learns that Alice has these 4 items, but he doesn't learn anything about her other items. That's the main idea of private set intersection. And one of the reasons I like this problem, PSI, is because of the many applications that it has in the real world. So when you look around at different applications of secure computation that people might propose in research papers, a lot of the ones that are the most realistic in my mind they seem to be applications of PSI. So next I'm going to share, I think I have 5 different examples on this slide. I think my favorite example or application of PSI is this problem called private contact discovery. So when you sign up for a new service, like an encrypted messaging application on your phone, one of the first things that it asks is it asks to see your contacts. And the reason it does that is because the service wants to know which of your contacts are already users of this service so that you can message them on this new application as you just installed it. So right now, for most applications that have this feature. It works by your phone sending your entire address book to the service. In the case of something like WhatsApp, it's owned by Facebook. So when you install WhatsApp, it takes the address book in your phone and sends it to Facebook. And most people are not happy with that. This would be a good place to use PSI, because the thing that they want to compute is the intersection of two sets, the intersection of the people that I know and the people who use the service. It's a simple intersection, but I don't want to reveal my entire list of contacts. You could imagine maybe there are some, maybe I have my doctor's phone number in my phone, or my lawyer's phone number, or my drug dealer's phone number, something like that. I don't want Facebook to know all these things. So this would be a good example for PSI. It's called Private Contact Discovery. Here is another application of PSI that's used. Many of these applications are used in the real world. Private Contact Discovery, people know about it, but it's not used in the real world. I'll explain why it's not practical yet much later in today's talk. But here is something that's used in the real world. So in the Chrome web browser, there's a password manager. So it stores all of your passwords. And one convenient feature that it offers is it will check whether any of your passwords were published online in breaches of. So when some company has its user database breached and posted online, the password manager will check whether any of your accounts were included in that breach. And the way it does this is by using PSI. The functionality behind this feature is to compute the intersection of my set of passwords and the passwords that are known about from account breaches. And here the privacy guarantee is pretty obvious. I don't want to send all of my passwords to Google in this case, since this is a feature in the Chrome web browser. So I don't want to send all my passwords to Google. I want to keep them encrypted in my password manager. So that's why the privacy of PSI is needed for this feature. Here's something that I've seen too much of in the last year. People email me these availability polls where everybody fills out the times that they're available so that we can find a common meeting time. This is a simple functionality. We just need to find the intersection of our sets of available times. But you can imagine wanting to do this more privately, where I don't have to share with everybody that I have so much free time in my schedule. This is actually true, because when I look at, I see many of my colleagues complain about how many Zoom meetings they have during the pandemic. And somehow I escaped without having too many Zoom meetings. So when you look at my calendar, it's pretty free. I don't have very many meetings. So then I feel guilty when I fill out these availability polls. I feel bad that I have so much free time in my schedule. So it would be nice if we could use private set intersection so that we could agree on a time to meet without feeling bad about how much time is in my schedule, or feeling bad about how you have so little time in your schedule. One other application that is actually used by Google is, Google is an advertising company. They make money by selling ads and displaying ads to their customers, or ads to their users. Their customers are the people who purchase the ads. And one way they like to measure the effectiveness of their advertisements is to compute the intersection of the people who saw the advertisement. That's information that Google knows. And then there's the set of customers who made a purchase at some store. And that's something that the store knows, or in some cases, Google works together with credit card companies to find people who made purchases at a particular store. So Google will not share the list of people who saw an ad, and a credit card company is not going to share, the set of all transactions that people made on their credit cards. But they can use private set intersection to figure out how many people saw the advertisement and then also purchased the item. And in fact, they usually want to learn a little bit less information than this. They usually just want to learn how many people there were. They don't want to learn which specific people it was. And they want to learn the sum of all of the total of all the purchases that are made. So I'll talk about that a little bit later. The last example is, this is specific to the United States. So in the United States, we have 50 states, and when you vote in an election, you register to vote in your state. And it's kind of decentralized. There's not a central authority for all of the United States that keeps track of the voter registrations. But it's illegal to vote in two different states, right? It's illegal to vote twice in the election. So it might be nice if two different states could check whether they have any people who are registered to vote in two states. So again, that's a simple intersection, but the states don't like to reveal their list of registered voters. In fact, President Trump tried to get all the states to send the voter registration to the federal government, and most of the states said, no thanks, we don't want to do that. So if they want to check for double registered voters, they would need, I think they would only be happy if they used private set intersection. Okay, so that's a lot of my favorite applications of secure computation, and they all happen to be applications of PSI. And I tried to show a wide variety of different applications. And in fact, many of these different applications, they're so different in their properties that they require different protocol techniques. So the focus of today's talk is just to show you many different protocol techniques that we use to make efficient private set intersection protocols. So what do I mean by these different techniques? I've grouped them into 4 different categories for today. So the first category is PSI for small sets. So think of the example of the availability poll, where we want to find a common time that we can both meet. So we're computing intersection of sets, and each set is the set of times in my calendar that I am available. That's probably maybe 50, maybe depending on how big the search area is, maybe it's 50 to 100 different 1-hour slots in my calendar. So it's PSI on small sets of maybe 100 items each. So when we have such small sets, there are certain techniques that are efficient and are practical. I'll talk about those first. When we move to PSI on larger sets, then we require different techniques. So if you think of the application to find people that are registered to vote in 2 different states, a typical state in the United States has maybe several million voters registered. So that requires an intersection of sets of size, a few millions. The techniques for these small sets don't scale very well to the large sets. And for that reason, we need completely different techniques. And I'll talk about those in the second part of the talk. The other set of applications that I talked about, for example, contact discovery and the password checkup feature for a password manager, those applications have sets of very different sizes. So the address book in my phone maybe has a few hundred people, but this application that I just downloaded on my phone, it maybe has millions or billions of users. Like I know WhatsApp has billions of users. So we need to compute an intersection between a very small set and a really huge set. And similarly, the password checkup feature, in my password manager, I don't have millions of passwords memorized. I have maybe hundreds of passwords memorized in my password manager, and there's billions of passwords that have been leaked on the internet, and we need to compute an intersection between those. This is much harder to scale practically, and it requires some different techniques that I'll talk about. And then finally, the application where I mentioned computing the intersection of people who saw an advertisement and people who bought a product. Like I said, usually we don't compute the intersection. We don't want to reveal individual people who bought the product, but instead we just want to learn some aggregate information about the intersection. We maybe just want to know how many people are in the intersection, or maybe we want to know what is the total amount that they spent. Right? So that's computing on the intersection instead of revealing the contents of the intersection. And those use even different techniques because now we're solving a different problem. And you can think that we're hiding more information. So we have to work a little bit harder in the protocols. So I'll talk about that last. So that's my picture of many different PSI techniques. My goal is to just show you many different techniques so that you can appreciate all the nice crypto ideas and also the nice combinatorics or data structure ideas that I find very interesting for PSI. And there's even more that I don't have time to mention. So you might want to compute an intersection where even if two items are very close to each other, then you want to say that they match. Maybe they don't have to match exactly, but maybe they're very close. Maybe someone has a typo in their name. And so if two names are different by one character, then you can say that they're a match. That would be fuzzy matching. There are some applications that use more than two parties. So in today's talk, I'm only talking about two-party PSI, but you can imagine that like in the application where we find a time to meet, often that's more than two people, right? We want to find a time that everybody can meet. So that's the intersection of many sets. And there's also private set union, which has other interesting applications. And all of these use completely different techniques, which is kind of interesting to me. There's a lot of similarity, but there's a lot of a variety of different techniques. So I tried to focus on what I see as the most fundamental techniques in this area, but there are many more that I haven't mentioned. So if you find this interesting, I hope you can think about these other problems also. Okay, so I promised I would start by talking about PSI on small sets. And the theme is, different application areas use different techniques. And the technique for this section is key agreement. So we can construct PSI protocols from key agreement in a pretty nice way. Before I talk about, so I'm going to show you your first PSI protocol, and you may have some idea of how these protocols might work, but there are some, a lot of times people come up with this bad idea for a PSI protocol, and I want to talk about that first so that I can explain why this is a bad model, a bad idea for PSI. So this is something that a lot of people who are not cryptographers, they come up with this idea. So Alice has a set of items and Bob has a set of items. They agree on a good cryptographic hash function like SHA-3, let's say. Bob hashes all of his items under this hash function and sends them to Alice. Alice also knows this hash function, so she can compute the hash of all of her items, and then Alice can just compare. She can just compare these sets of hashes. And if she sees a hash from Bob that she recognizes, then she knows which of her items has that hash value. Okay, this is something that people, this is an idea that people come up with and they implement this, but it's not secure. And the reason is, let's imagine that these items are phone numbers. In the United States, a phone number is how many digits? 10 digits long. So there's maybe 10 billion possible phone numbers. Well, 10 billion is not that big of a number. It would not take very long to compute a hash of 10 billion different things. And if Alice computed the hash of all the phone numbers in the world, then she could compare, she could just look at Bob's protocol message and figure out everything in his set. So we'll call that a dictionary attack. So for every item in the dictionary, compute the hash of that item. And so when the dictionary is small, for example, the set of all possible phone numbers, the set of all possible time slots in May in my calendar. It's a very small set of items. This protocol gives no privacy for Bob. It totally leaks his input. So we don't want to do that. In fact, even the United States federal government knows that simply hashing data doesn't make it private. So this is a common problem in many areas, but specifically it's a problem in PSI. So we need to do better than this. So here's a better mental model for PSI. Instead of computing a public hash function on all of Bob's inputs, you can imagine that Alice and Bob have to interact to evaluate some function on Bob's inputs. So in this slide, there's a function f, and somehow f involves some private secret that only Alice knows. And it may also contain a secret that only Bob knows. And that means that Alice and Bob have to interact in order to evaluate that f on their inputs. Right? So we've gone from a public function h to a function that can only be evaluated by Alice and Bob interacting. So that means that if Alice tries to do this dictionary attack, she gets stuck because she can't go through the dictionary and evaluate f on every item in the dictionary because she needs to interact with Bob in order to evaluate f. And Bob doesn't stay available to let Alice do this. So Alice is bound to whatever inputs she used in this interactive phase. Those are the only outputs of f that she can learn, and she can't learn the entire dictionary and evaluate them through the function f. So that's the mental model. So we need a function that requires interaction to evaluate. So that's what we're going to do next. So I want to show you how this can be done and why it's related to key agreement. I want to start with the simplest example where Alice and Bob each have just one item. So if you think about PSI, where each party has one item, then the challenge is to determine whether their items are equal. So they want to learn whether x equals y in this example. And if x is not equal to y, then they should learn nothing about each other's inputs. Okay. So here's a nice trick. This trick goes back to the 80s, but I think the first time it was, it was used for PSI first in the 90s, but this idea comes back to the 80s for sure. So what I drew here is, it's supposed to look like Diffie-Hellman key agreement. So in Diffie-Hellman, Alice would send G to the A and Bob would send G to the B. So that's what they do here, except instead of G, they use the hash of their input items. So Alice sends h of x to the A, Bob sends h of y to the B. And if you think about Diffie-Hellman key agreement, what does Bob do when he gets G of A from Alice? Well, he raises it to the B power. So he can do the same thing here. He can take Alice's message, raise it to the B power, and now he has h of x to the AB. And Alice can take Bob's message and raise it to the A power. And now we have this Diffie-Hellman looking situation. And the protocol says Alice should compare these two results. So h of y to the AB and h of x to the AB. And obviously if x equals y, then these two group elements are equal. And it's not too hard to see that this is secure, but I just want to point out that this fits into my previous slide because they're interactively evaluating the function h of x to the AB power. And you must evaluate this function interactively because A and B are secrets that are just known to Alice and Bob. So no single party can evaluate this function by themselves. They need interaction, right? But we evaluate this function on X and Y, and then we compare the outputs in the clear. So to see why it's secure, I want to argue that if X and Y are different, then if X and Y are different, then let's say that the protocol hides Bob's input. So the only thing that Bob sends that depends on his input is h of y to the B. So in the random oracle model, h of y is going to be a random independent group element. And the Diffie-Hellman assumption says that if you take a random group element, raise it to the B power, that's indistinguishable from random, even if you're using that B exponent for other things. So Bob uses the B exponent here as part of, I hope you can see my mouse, but he uses his B exponent in two places. So even though he uses the same exponent in two places, h of y to the B looks random. And that means that the protocol hides Bob's choice of y when X and Y are different. Okay, so that's the special case of PSI when they each just have a single item. Suppose they have many items and they want to compute the intersection. Well, they can just do this idea, many different times, but always using the same exponents. So Alice hashes each of her items. She raises them all to the A power. Bob hashes all of his items, raises them to the B power. And he also takes all of Alice's items and raises them to the B power. And then Alice can compare. She can raise all these to the A power, and then she can compare. So again, they're evaluating this function, h of x to the AB. They're evaluating it interactively on all of their items, and then Alice compares the outputs. Okay, this is a classic protocol, like I said. The ideas in this protocol go back to the 80s, but I think the first time it was explicitly written down as a PSI protocol is from this paper in 1999. The protocol that I described is secure against semi-honest adversaries. So it works if everyone follows the protocol. If you want to protect against malicious adversaries, it requires some zero-knowledge proofs. There are various papers that show how to do this. There are some papers that authenticate the items. So, for example, this Alice can only include an item in her set if she has a signature for it from some, certificate authority. There are extensions that do that. And I have a work in progress with my former PhD student, Ni Triu, where we show how you can do this from any key agreement, basically. It doesn't have to be based on Diffie-Hellman. And we show some different approaches for getting malicious security as well. That's something that's in progress for us. for all of these, I want to give you a sense of how efficient or how expensive these protocols are. PSI on small sets is very, very cheap. So if each party has 256 items, our latest protocol achieves malicious security. It takes 1/10 of a second of time, and it takes only 10 kilobytes of communication. So very, very fast and very low communication when the sets are small. So this is something that I think anybody could be doing today if they have an application for PSI on small sets. Okay, that's the end of small sets, and I'm going to move on to PSI on large sets. So I apologize because we're going to quickly move to many different techniques. So PSI on large sets. So what goes wrong when the parties have many items, let's say 1 million items? So if you take the previous protocol where, based on Diffie-Hellman, the first thing that Alice should do is hash all of her items, raise all of those values to the A power. So if she has 1 million items, then she needs to perform 1 million exponentiations. And exponentiations are fast, but if you have to do 1 million of them, it's expensive. So even this step, I had some of my students estimate how much time this would take. They said it would take 4 minutes using a really fast elliptic curve and really good exponentiation. Even just doing the first step of the protocol would take several minutes. And we can do better than that. So I'm going to show you how instead of 4 minutes, we can do it in 4 seconds if the parties have 1 million items. Okay, so this part of the talk is going to have the most technical details because this is a nice combination of crypto tricks and data structures tricks, and I want to share that with you. Okay, so the main ingredient that we use in these kinds of PSI protocols is something called batch oblivious PRF. So what does that mean? So I want you to imagine many different slots. So I've numbered the slots 1, 1, 2, 3, and so on. In each slot, Alice has an item. And batch oblivious PRF means that in each slot, the parties generate some random function. So the first slot, there's a function f1. And Alice learns f1 evaluated on her item x1 in that slot. And Bob learns the entire function. So that means he can evaluate f1 on any input that he wants. Okay. Bob learns nothing about Alice's items, these x values. And Alice only learns, in each slot, she just learns one output of f. And all the other outputs of f look random to her. By the way, this is very similar to OT extension. In fact, you can build this from the OT extension tricks that I talked about last week. So these x values are like Alice's choice in the oblivious transfer, and all the possible outputs of f are, the OT messages that she could choose from, and she chooses to learn just one of them. And now we have many instances of that. It's like a 1 out of n OT for a very large value of n. Okay, so this is something that I hope looks reasonable, believable that this could be done. And this is very efficient. So because it's built from OT extension, we can generate, millions of these instances, a million slots of batch OPRF in just a few seconds. Okay. So how do we use this tool to do PSI? Okay, so I'm going to show you the protocol outline. So I'm going to describe this paper of ours from 2016. It's called the KKRT protocol, but I'm going to describe it at a high level. And at that level, it's basically also the same protocol as this Pincus Schneider Zoner paper from Usenix 2014. Okay, the difference between these two protocols is it doesn't really show up on these slides. So this is just a high level picture. Okay, so in this example, Alice and Bob each have items, and they choose some number of bins. In this case, there's 10 bins, and they agree on some public hash functions, two hash functions that hash items into bins, right? So what I mean is item A gets associated with two bins. So H1 of A is 2 and H2 of A is 7. So that means item A is associated with bin number 2 and bin number 7. And item B is associated with bin 3 and bin 9 in this example. Okay, so everybody takes their items and associates that item with two bins. And these hash functions H1 and H2 are public. So if we can see in this example, we know that Alice and Bob both have the item C. So that both Alice and Bob map the same item C into the same two bins, 3 and 7 in this example. Okay. There's a hashing technique called cuckoo hashing, which says if you have a large enough number of bins, then there is a way for each item to choose which bin to place it, so that each bin contains only one item, right? So in this case, item A has two places it can be placed. Item B has two places that can be placed. And cuckoo hashing says there's always a way to place those items, to choose which position to put them, so that each bin has at most one item. So I've drawn that example here. So Alice chooses to put item A in bin 2 instead of bin 7. She places item D in bin 7 instead. Okay, so I've drawn that there. That's cuckoo hashing. If both parties did cuckoo hashing, they might place the items in different places, right? Bob has item C. He doesn't know whether Alice is going to place C in bin 3 or bin 7. So if he uses cuckoo hashing, he might place it in a position where it won't match where Alice placed it. So we have Bob do something different. He's going to place each item into both of its possible locations. So here he has item C. He placed it in both bins 3 and in bin 7. So now some of Bob's bins have more than one item, but Alice's bins only have at most one item. Okay, so they use this hashing trick to place their items into bins in this way. And now they run this OPRF in each bin. So in each bin, Bob learns a random function, which he can evaluate on any input that he wants. But Alice learns in each bin. So she had item A in bin 2, so she learned the output F2 of A. It doesn't really matter. So in this picture, it doesn't matter what Alice puts in bin 1 or bin 4, 5, 6. So I haven't drawn it because it doesn't really affect anything here. Okay. So Alice learns, in each bin, Alice learns just one F output. Bob learns all of these F functions. So now what can they do? So Bob can look at all of his items in all of the bins and compute the corresponding F output. And I'll just show you by examples. He has item C associated with bin 3, so he can compute F3 of C, and that's what he sends to Alice. Item E lives in bin 3, so he sends F3E, F4D, and so on. So, and it's important to note that Bob is, for every item that Bob has, he placed it in two positions, and so he sends two F outputs for each of his items. And now what can happen, Alice can look through this list of messages that Bob sent, and she can look at which ones she recognizes. So in this example, she only recognizes F3C and F7D, and all the other values here look random, right? That was the guarantee of these F functions, right? Any value of any output of F that I didn't list here for Alice will look random to her. Okay, but she sees two values that look familiar, so she can conclude that C and D are in the intersection. And that's essentially the entire protocol. So I hope that makes sense. Feel free to ask questions anytime in the chat or the Q&A feature. I figured out how to have it visible on the screen. So that's what I described to you is the state-of-the-art, fastest, semi-honest PSI protocol. Okay, it's only semi-honest secure, so it's not secure against malicious players. And I want to illustrate some kind of an attack that happens if the players are malicious. So one of the important properties of this protocol is that Bob is supposed to send two values for every item. So in this example, item C is assigned to two different bins, 3 and 7. So he should send F3C and F7C. That's what the protocol says. But if he's malicious, he might choose not to do that. So let's imagine that Bob only sends one of these two possible values. He sends F3C, but he doesn't send F7C. Let's see what effect that has on Alice's output. So let's just step through the protocol and see, and let's see what happens. So Alice has item C. I want to know whether she includes it in the output. Well, she might put item C in bin number 3. And if she does that, then she will recognize F3C in Bob's message, and she will say, yes, item C is in the intersection. But it's also possible using cuckoo hashing that she places item C in bin 7. So she learns F7C. She doesn't recognize F7C in Bob's message. So she concludes that C is not in the intersection. Okay, so sometimes she thinks C is in the intersection, sometimes she doesn't think that. The problem is the choice of whether she puts item C in bin 3 or bin 7, it depends on all the other items in her set, right? Because of this, in cuckoo hashing, I place each item in a different position based on all the other items that I have. It's kind of some global property. And that makes it basically impossible to simulate the effect of this attack in the ideal world. Right? In the ideal world, in the ideal world, the adversary can't say, oh, I want to include an item C in my set, but only if the honest party has some items that cause the cuckoo hashing to do this. Otherwise, I don't think the item C should be in the output. It just can't happen in the ideal model. So it's not a devastating attack. It's not an attack that breaks privacy, but it just can't be proven secure in the normal way. So that's the main problem. That's what prevents this protocol from being secure against malicious parties. So that's kind of interesting. So I want to talk about some relatively recent work where we overcome this problem. So this is a work with my co-authors from Eurocrypts of last year. And we came up with a way to fix this problem, which I also think is interesting. So that's what I'm going to tell you about. If we want to consider malicious PSI or make this existing protocol malicious secure, we need this batch OPRF primitive to be secure against malicious adversaries, right? So this is kind of like an OT extension thing. It needs to be secure against malicious. The good news is that it costs almost nothing to make these malicious, to make OT extension protocols malicious secure. And we talked about that last time, right? So the cost to make it malicious secure is to just check like a random linear combination of all of the OT messages and check them for consistency. and it's pretty cheap. And one of the properties that we used in that observation was that the values in these different bins, so I'm going to use the language of OT extension because that's what I talked about last time, but the OT values in the different bins, they have this additive homomorphism property. Okay, so in the language of OPRF, so FIX is the OT output. So if Alice chooses to learn X, she learns FIX in bin I. If you XOR these values from different bins together, you get something. You get something reasonable. So if you just think back about that OT extension business, there was a step where we used the fact that there was some linear error correcting code, and the linearity of the code made things add up nicely together. So I don't want to get into those details about why this is true, but we have this property that if you take FIX plus FJY, you get the result of some new function, Fij, evaluated at x plus y. So Fij is some new function. It's different than all of these other f functions, but it's something that Bob can compute. So if you tell Bob the value, the indices ij, then he can compute a function Fij on any input that he wants. Okay. And also, if there's an Fij value that Alice can't compute by using these XORs, then it will look random to her. So kind of the natural thing that you would expect. So we use this additive homomorphism property in what I think is a nice way. So here's the main idea of the protocol. Again, we have this similar structure where each item is mapped to two different bins. So previously, Alice had an item assigned to bin 2 and bin 7, and we would say she should choose which of those two places to put her item. Instead, what we will say is she should secret share her item between these two bins. So she places some S2 in bin 2, and she places S7 in bin 7, and S2 and S7 are additive shares of her value A. So she does that for all of her items. So she secret shares B into two shares, and she places those shares into bins 3 and 9. Okay? And she does that for all of her items. Good. Now they do the usual OPRF in each bin. And this is what Alice learns. And now I'm going to, let's observe what Alice can do with these values. She learns F2 of S2. She learns F7 of S7. And we have this property that if you add these two together, they have this homomorphic property. So you would get F27 of S2 plus S7, but that's just A in this case. So she can learn F27 of A. She can learn F39 of B because item B lives in positions 3 and 9. And so she can learn these 4 values. Okay. And now Bob can do something slightly different. He has item C assigned to bin 3 and bin 7. And so, like I said, he can compute the function F37. So he sends F37 of C, F47 of D. So you can see where this is going, right? And the important thing here is that Bob sends only one F value per item. That was what we were trying to avoid. And this is how we avoid it. So now you can see Alice will recognize 2 of these values. She recognized F37C and F47D. So she concludes that C and D are in the intersection. So from if Bob is malicious, it's a lot easier for the security proof to work now because he can either include F37C or he doesn't include it. So that makes it easy to explain the effect that he has on the honest party. He can't include C in his set halfway. He can either include it or exclude it, and that matches the ideal world for PSI. You either have an item or you don't in the ideal world. So that's how we overcome it. There are some interesting data structure questions that come up here. So I said that Alice should secret share all of her items according to these, the placement of the items in the bins. She should secret share them in this way. So how exactly does this work? Right? Because this involves solving some system of linear equations. So here's one natural approach. So let's set one position arbitrarily. I set S2 arbitrarily. Then I find an item. So each item has like 2 locations. And I want to find an item where one of the locations is not determined yet. So item A has position 7, which is not determined yet. That means I can solve for the S7 that makes this work, right? So I solve for S7 so that S2 plus S7 equals my desired value. And then I just repeat. So now item C has one of its positions unset, so I can solve for the S3 that gives the right answer. Now item B has one position unset, I can solve for that, and then item D, and I'm done. Induced by these arrows is acyclic. So this is called the cuckoo graph because it's related to cuckoo hashing. But you see I've drawn an edge between, let's say I've drawn an edge from S9 to S3 because there's an item that gets mapped to bins 3 and 9. And in this case, the graph was acyclic, so I could step through the graph in this way. But if there's a cycle in this graph, then maybe you can see why this process won't work. So we have to figure out how to deal with this in our paper. So here's the problem that we have. We want to find a vector of items, these S vector, and the vector should satisfy a bunch of these linear constraints. So for every item X, if I look at H1 of X and H2 of X, those positions of the vector should XOR to my value X. Okay, but it doesn't have to be, in order for this protocol to work, I don't need this to be just 2 positions. So the way I showed you is for each item, I probe 2 positions of this vector and I XOR them together. The number doesn't have to be 2. Then it could be any set. So here I said, it would be okay if I had a data structure that worked like this. If I want to, if I take an item X and I probe it at some set of positions, so that's like P of X, and I XOR those positions of the vector, they should give me the value X. So for every item X, I have this I have this linear constraint, and those linear constraints must be satisfiable. So I can't have like degenerate or linearly dependent constraints. They need to be all linearly independent in order for me to generate a solution, right? So we need that property. We need the size of this vector to be small because the size of this output vector is the number of OPRFs. It's the number of slots. And that is that tells us the communication cost of the PSI. Ideally, this should be linear in the number of items. And it's not just enough that this system of linear equations can be solved, but it needs to be solved efficiently in linear time, right? In the worst case, solving a system of linear equations could take cubic time, but that's too slow for a PSI protocol. You don't want to solve a system of 1 million equations in cubic time. So we need these P sets to be a certain structure so that the set of linear constraints is independent, but also can be solved efficiently. So I don't have, I don't have enough time to go into how we do this, but we found it to be an interesting combinatorial problem, and we did find a nice way to do it. And it almost works like what I described here. So most of the algorithm works by following this approach of just setting one item at a time. But then we deal with the cycles separately in another step. So you can check the paper for more details about that. And we also have a paper that was just accepted to crypto that should be on ePrint in the next few weeks, where we have a slightly better data structure for this. Okay. So that was kind of the most technical part of the presentation, where I really wanted to show you the details of one of these PSI protocols. And like I said, this is a very efficient approach for PSI. So if both parties have 1 million items, then if you want semi-honest security, it takes about 4.5 seconds and 128 megabytes of communication. If you want malicious security, it's just a slightly more. It's not very expensive at all. The gap between malicious and semi-honest is very small. So a little bit slower and a little bit more communication, but still pretty reasonable and practical. And those numbers are from our upcoming paper using the best data structure that we know about. So that finishes the section on large sets. And I see that there is a question. There's a question in the chat. Well, there's a question in the Q&A that's in English, so I'd be able to answer that. There's some comments in Mandarin also that if those are questions, and I hope someone can translate them for me. But the English question is, does batch OPRF mean that it can generate lots of OPRF values with different keys at one time? Yes, so that's exactly what it means. I'll just show this picture. If this F function has just a single input bit, then each F function has two outputs, F of 0 and F of 1, and Alice chooses which of those to learn. And that's exactly 1 out of 2 OT. And so the problem of generating millions of these is kind of like the problem of generating 1 million instances of 1 out of 2 OT, which is what I had talked about last week. So yeah, all of these different F functions are essentially independent, although they do have this additively homomorphic property. Okay, so I hope that answers that question. Does your new work still need random oracle model in security proof? Yeah, so all of these protocols require random oracle. I'm trying to think. Okay, now you're making me think about the entire security proof. The semi-honest one, I'm going to say, does not require random oracle model. That's what I want to say, and I think it's true. The malicious one definitely needs random oracle model, because actually I cheated a little bit in this picture. So Bob doesn't send just these values. He sends a random oracle hash of these values. So think of like H of D, comma, F47 of D. And we need that so that the simulator can extract. The simulator needs to look at this value and realize that it corresponds to an item D, and the random oracle model helps us. So the new work still has that property. That's something I don't know how to I don't know how to overcome that. But yeah, the malicious ones use random oracle. Why not use the same OPRF K for all elements? Oh, that's a great question. Why not use the same OPRF for all elements? Yeah, if we knew how to do that directly, then we would have a much simpler PSI protocol. And that protocol would look just like the simple Diffie-Hellman one from before. Yeah, it will take me too long to move my slides there. But yeah, if we had a single OPRF that could be evaluated on many inputs by Alice, then you would have a very simple PSI protocol. The problem is we don't know how to get an OPRF, a malicious secure OPRF like that. So just to be clear, we know how to get OPRF where Alice can evaluate the OPRF on a single item. That's what this is right here. Alice evaluates OPRF on a single item. And the problem is to get PSI from that. If you have an OPRF that Alice can evaluate on many items with this, with the same OPRF key, then PSI becomes very simple. So I think I like that question. So you have the right idea. We just don't know how to get that directly. In fact, you can view all of our protocols as a way to transform a simple OPRF where Alice just can evaluate on one choice, and we use that to build an OPRF where Alice has many inputs. So that's a great question. If the set is large, how is the hashing idea at the beginning of the talk insecure? Yeah, that's a good question. So yeah, so like you're saying, if the dictionary is large, the problem is that the security definition means that the protocol must be secure even if the attacker has a good guess about what the items are. So it's true that hashing-based protocol that I said was a really bad idea. If the items are really unpredictable, then that protocol is secure. Because if the items are very unpredictable, then the attacker will never evaluate H on one of those items. But the usual security definition says the protocol should be secure for all inputs, even inputs that the adversary chooses. If you think about the normal definition of encryption, we don't say that the encryption scheme is only secure if the plain text is really random looking. We say encryption is secure even if the adversary chooses the plain text that you're encrypting. And MPC protocols have the same property. So we need to build protocols that are secure even if the attacker is choosing the honest party's inputs. And of course, if the adversary is choosing them, they will not be unpredictable. And so that hashing-based protocol will lead to problems. But yeah, if you somehow have a situation where you're only computing PSI of really unpredictable values, then you could use the hashing idea. But yeah, it just is not the standard security definition. These are great questions. Thank you for all of these. How to realize two-sided output in them? Wow, these are some great questions. So there's a question about two-sided output in the malicious model. So thanks for that question. So yeah, I think you observed that in this protocol, Alice is the only one who gets output, right? All of the information is going from Bob to Alice. All of the PSI protocols I know in the malicious model have this property that only one party gets output. And actually, this is a very challenging problem. How to get both parties the output. It's not secure to have Alice. So Alice learns the output here, and you could try to tell Alice to report the output back to Bob, but she can lie, and she can lie in ways that are very difficult to protect against. I think that's an open research problem, to take these really efficient protocols that work for millions and millions of items and make them secure with two-sided output. So both Alice and Bob learning the output. This is something that I've thought about over the last few years. I talk about it with my students quite a bit. But so far, I believe this is a very challenging problem. So it's a great research question. If you're interested in this research area and you want to have a question to work on, I think that's a good one. But yeah, I don't know how to do this efficiently. Wow, so many questions. Are the techniques for PSI and PSU largely exchangeable or quite different? Yeah, so he's asking about intersection versus union, and the techniques are very, very different. So I only know of 2 protocols for PSU, and they're just very different. And, you know, when I'm writing a paper about PSU, I try to explain why PSU is so different than PSI, and I always find it very difficult to explain. And sometimes the reviewers find it very difficult to understand. But so the techniques are very different, and I don't really have a great explanation why. Yeah, it's still very confusing to me. So I don't have a great answer for that. I wish I did, but yeah, I guess you didn't ask why they're different, but you just asked if they're different. And yeah, I would say some of the hashing tricks are similar, but some of the hashing tricks just don't work. Like this cuckoo hashing thing, I don't think it works for union for some reason. And it's just, they're very different. It seems like they should be similar, but they're very different. And yeah, I wish I knew why, but that's a great question. Is there a batch homomorphic and? Yeah, so I think the question is asking about this homomorphic property, and it's homomorphic under XOR. I don't know of anything that's homomorphic in a different way, but the reason it's homomorphic this way is just because that's how OT extension protocols work. And yeah, we just had a flash of insight where we realized this, that this could be useful for PSI, but I don't know if there's anything that's homomorphic in different ways, unfortunately. You know, maybe homomorphic over a ring or a field, so it's not maybe just XOR, but like addition mod P. I think there might be some homomorphic things in that way, but not homomorphic with respect to AND operation. So there's a question, how do you ensure homomorphism of keys? Yeah, so in this slide, like I and J are kind of like different keys. So for that question, I would just say that the equation that I wrote on this slide is a big simplification to what actually happens. So it's not really a homomorphism of keys. So you shouldn't think of I and J as keys. Like I and J are just, you know, identifiers, like function number 1 and function number 2. And Fij, so ij is just a different identifier. But it's like ij itself is not a key. It's not like I take I plus j or something and get a new key that's I plus j. So I've made too many simplifications of this equation just to have it fit in the slide and make sense. But it's not really homomorphic with respect to the key. It's only homomorphic with respect to you know, these X inputs. But it's also with respect to a different function that Bob can compute. So if he knows I and J, then there's a function that he can compute. It's not the function where he takes his keys for I and J and adds them together and gets a new key. Well, it kind of is, but it's a little bit more complicated than that. So it's not fully homomorphic in the way that it looks in this equation. I've simplified too much here. Okay, and then we have a report that my students' implementations are not compiling well. Can you?
This question is beyond our lecture, so
yes,
yes. To answer it.
Yes, yes, I will let them know. Thank you for that. Send us an email, and then it will make it more likely that we can remember to do that. But yeah, we like to hear about any problems that you have. Okay, I think I have about 20 minutes. I have about 20 minutes left. Thank you for all those questions. That was enjoyable for me. So let's move on to PSI on sets of very different sizes. Yeah, some interesting applications achieve this, and again, completely different techniques in a situation. So in the example of contact discovery, we have my address book in my phone with maybe 100 or 1,000 people, 100 or 1,000 phone numbers. Something like WhatsApp has over 1 billion users. If we think about the password checkup feature, my password manager has maybe 1,000 passwords in it. And this website that keeps track of all the breaches, it has, when I took this screenshot, 10 billion leaked accounts. So very huge sets that we want to do PSI. So there's two different ideas that people have proposed to deal with these huge sets. Okay, I'm just going to describe them at a very high level, just to give you a sense of how people approach this challenge to deal with billions and billions of items. So let's go back to that first Diffie-Hellman-based protocol. And now imagine that Alice has hundreds of items, but Bob has billions of items. Okay. If Bob has billions of items, let's look at the protocol message and which part of the protocol scales with his billions of items. Well, it's just this part, this H. He hashes each of his items and raises them to the B power. That's the only part of the protocol that is affected by having billions of items. So the idea here is to notice that this part of the protocol that I put in a circle, it doesn't depend on any of Alice's inputs. So actually, it can happen, this can happen in an offline phase. What I mean is that Bob can compute this message and he can just post it publicly on the web, or he can include it as part of the app on the phone. So when you install the app on the phone, the app contains this big message, this big PSI message, as a file within the package. And the rest of the protocol will still work. And in fact, one thing that's interesting is that it's safe. Usually you think of, if Bob runs a PSI protocol against all these different users, he should use different randomness for all these different PSI protocols. Well, it turns out in this case, it's safe for Bob to use the same exponent for many different PSI protocol instances. And one way to see that that's true is that this is basically Diffie-Hellman. And if I run Diffie-Hellman with 100 different people, I can use the same exponent in all of my Diffie-Hellman key agreements, right? I can just publish G to the A, and everybody can send me their different responses, and I'm safe, right? So the reason that works for Diffie-Hellman means that it also works here for PSI. So here the challenge is really about how to encode this message. So this is still a huge message, and now you can think about different ways to encode it to make it as small as possible. I cited this paper here from a few years ago that studied this problem and came up with different, the best encodings for this huge message. It's still very large. So if Bob has 1 billion items, then this big offline message is 4 gigabytes. But this is one way around it, because there's 4 gigabytes that's public and shared for everybody, but then the actual online part of the protocol only scales with the size of Alice's set. You see, there's only X values here. Okay, so that's one idea. It's not great because you still have this huge message, but it's a helpful observation, definitely. And depending on the size of Bob's inputs, it might be a good solution. Another idea is to allow some leakage. Usually we want PSI protocols to be completely secure and leak nothing, but sometimes it might make sense to trade performance for a small amount of leakage. So here's one way to allow leakage. So Alice has 100 items, Bob has 1 billion. They agree on a way to map items into bins. So imagine there's 1 million bins. They agree on some hash function H, and each person places item X into bin H of X. Okay, so and the output of H is whatever 20 bits. So you have like a million possible outputs of H. So Alice has 100 items into 1 million bins. So most of her bins are empty, right? So I draw it like this. Bob has 1 billion items into 1 million bins. So each bin has roughly 1,000 items. So I draw it like that. And now the leakage is Alice just tells Bob, hey, these are my non-empty bins. She just gives the name of those bins. So she says, oh, bins number 3, 4, and 5, 6, 7, 8, 9. Bins number 3, 4, and 9 are non-empty. And then they just do PSI only on those bins. So the way I drew it here, Bob has these million bins, and he only inputs the active bins into the PSI, and they just do a normal PSI, nothing special. But now it's a PSI between 100 items for Alice and roughly 100,000 for Bob. These are just example parameters, obviously, but there's 100 active bins. Each bin has roughly 1,000 items, so 100,000 items. And this is very fast. This is less than 1 second. You can do this. So very, very efficient. And there are, depending on what kinds of items you care about and the privacy of those items, you might consider different ways to hash the items. And so there's a nice paper about how to choose which hash function to use here. So they were specifically looking at the case of passwords. And they said, what if these items are passwords and Alice doesn't want this leakage about her set, right? Her message is leakage about her set input items. She doesn't want that leakage to increase the attacker's ability to crack her passwords. So there's a well-defined way of defining, the security level of passwords in terms of how long you expect the adversary to guess one of the passwords, and then you can measure how much this leakage increases the adversary's success at guessing passwords. So it's a very specific analysis in that paper. It's very interesting. So those are just two very simple, high-level ideas. And I have some numbers that I took from those papers. So for this paper about this offline preprocessing, the offline step is expensive. It's a gigabyte, right? But the online phase is very fast. I guess, just a few seconds. And for this example that I had on the previous slide, this is using some leakage, right? So this first example is no leakage, but an expensive offline message. And this other example is allowing some very minor leakage about the inputs, but a quarter of a second and only 1 megabyte. So it's possible to trade off on these. So that's how people in practice, that's how we get these features like this password checkup feature. Google's password checkup feature uses this approach. It has a very small amount of leakage in order to make it practical. Okay. So the very last thing, I just have a few slides on computing on the intersection. So this is an area that's we know much less about making efficient protocols. So I just want to show you roughly how these protocols work, what the challenge is, and I just have bad news that it's much slower than these other kinds of PSI. But there's one situation where you can compute on the intersection very nicely. So here's the original Diffie-Hellman PSI protocol, and it reveals the contents of the intersection. And why does it do that? Because suppose Alice raises all these values to the A power, and then she notices that this first value from Bob is familiar. And so then she concludes that, oh, it must be because X1 was in the intersection. And she concludes that because when Bob raises these values to the B power, he preserves their order, right? So I wrote these in the exact same order as they were sent from Alice. So that means Alice can identify, okay, the first one corresponds to my input X1. The second one corresponds to my input X2. So that's how she recognizes the intersection. If we just let Bob shuffle these items, then Alice will see, hey, there's a value that looks familiar. So I know that there's some item in the intersection, but these have been shuffled and I don't know which one. I don't know whether this corresponds to my input X1 or X2 or anything. So basically Alice learns the cardinality of the intersection. She learns how many items are in the intersection, but she doesn't learn which ones they are. That's like a really simple trick. It doesn't really affect the efficiency of the protocol, but it hides much more information. And so that's really nice. The problem is this trick only works for the Diffie-Hellman PSI protocol, and it doesn't work for any other PSI protocol. So it just doesn't work. All these protocols built from this batch OPRF, there's no way to kind of shuffle things, unfortunately. So I can show you the state of the art for computing on the intersection. So there's a step where, so there's an interactive pre-processing step. So yeah, just because I'm trying to make this a simple slide, I'm not going to show the details, but this paper by Benny Pincus and others gives a method for Alice and Bob to take their inputs, and then they learn a bunch of strings. And if Alice's input Xi is in the intersection, then the corresponding string Ri and Si are going to be equal, okay? So that means if you want to know the intersection, you just have to check these n pairs of strings. So the important thing is it's the same subscript here, Ri and Si. If you just wanted to compare all the X's and all the Y's, you would compare Xi to every Xi to every Yj. That would be n squared comparisons. But because of this pre-processing, you only have to compare R1 and S1, and then compare R2, S2, and then you only need to do these linear number of comparisons. So then you do a generic secure computation protocol just to do those linear number of comparisons, but you do it inside of a generic MPC protocol to keep the results of that comparison secret instead of revealing it. And then you can compute the function on the result. So it turns out to be very slow. It's much more expensive to compare two strings inside of a generic MPC protocol. Just think about like garbled circuits or something. It's much more expensive than the tricks that I've shown you here today. So the bad news is if you have 1 million items and you just want to compute the cardinality of the intersection, it takes 2 minutes, 2.5 gigabytes using this state-of-the-art protocol. And that's 20 to 30 times worse than just a plain intersection, right? So if you want to reveal the contents of the intersection, it takes maybe 4 seconds and 100 megabytes. If you want to hide the contents of the intersection and only reveal the number of items in the intersection, it's 20 to 30 times more expensive. So there's a big gap there. It's a big challenge to close this gap. That's another really good research area if you're interested in this topic. So here's the summary. We have PSI on small sets, large sets, asymmetric sets, and we also have computing on the intersection. All of these different applications of PSI use very different techniques. I hope you enjoyed learning about many different protocol techniques. But that's the end of my slides. That's my last one. So if there are any more questions, I'm happy to take your questions on the Q&A or spoken questions are good too. And before we get to the questions, I just want to say, thank you for attending all of these lectures, and it was just a great pleasure to be able to share this exciting work with you over the last few weeks. I look forward to it, every Thursday. A good way to end my Thursdays here, in my time zone at least. So I just want to say thanks you, and thanks to the organizers and to the Shanghai Institute, and thanks to you for inviting me. I really enjoyed it. So I see some questions. This looks like a math question. If Bob sends h of y to the b and h of x to the ab, and Alice finds h of y to the b equals h of x, why can't Alice get b since she already knows h of x? I think this is a question about discrete log. So this would be a common, a common property of any Diffie-Hellman approach, that it should be hard to, this b is in the exponent. So if you see h of x to the b, it's hard to learn that exponent, even if you know the base. So that's like a common, it's a common property of any of this Diffie-Hellman stuff, that it should be hard to compute a discrete log. So I think what you're asking is, why can't they compute the discrete log? And so the assumption is this, we're using a cyclic group where that should be a hard problem. How to efficiently change an unbalanced PSI when the client set is much larger than the server set? Oh, I see. So I think this question is about this unbalanced setting. And the question is, who gets the output? So yeah, in this example, Alice, who's the client, gets the output. In this example, it doesn't really specify, because I just use any PSI protocol that I want. So I can make either party get the output in this example. So I think that answers your question for this picture. I could choose a PSI protocol that works in either direction. That's fine. In this one, let's think. Yeah, this one is maybe asymmetric. So it's hard for me to think on the fly here. I think it only works in this orientation, because if we put the X stuff, if we make the X values happen offline, then you still have this other stuff that needs to happen in the online phase. So I think it only works here. So I think that's a good question. I don't know exactly how to change this so that Bob is the only one getting output. That's a great question. I don't know. That might be an open research question. I don't know how to do it that way. Good. I don't see any other questions in the Q&A. Do you have any questions in person, Yu?
Thank you for the very informative and educational talks, and I'm sure we will all benefit from it. So
I just want to say, anybody who's watching, if you're interested in this kind of thing and you have more questions about secure computation, garbled circuits, OT extension, PSI, please email me. Just say that you saw me on these talks, and if you have questions, email me, and yeah, I'll enjoy hearing from you.
And I look forward to inviting you to more advanced topics in future. So don't say no.
Yeah, maybe I can come in person.
Yeah, sure.
It'll be nice to see you in person again.
Okay, let's thank Mike for this very wonderful series of talks. That's the lecture for today. Thank you, Mike.